To present our first speaker, I'd like to invite Bill Crossley, the William Uhrig and Anastasia Burna's Head of Aeronautics and Astronautics. Over to you, Bill.
Great. Thanks, Arvind. Well, so it's my pleasure to introduce Haifeng Wang, who got promoted this August to Associate Professor in Aeronautics and Astronautics. Haifeng joined us in 2012 after earning his PhD in 2010 and then a two-year postdoc stint, both at Cornell. Haifeng works in turbulent combustion modeling for propulsion energy systems. He does a lot of work in theoretical and scaling analysis and modeling of differential molecular diffusion and turbulent combustion. He's also done a lot of work to advance the transported portability density function methods that are used for turbulent combustion. So obviously I've got the right introduction because that's the title of his talk here. Here at Purdue, Haifeng has also been very instrumental in introducing our junior level course in thermal sciences. As propulsion has become a big part of what Purdue does and a big part of aeronautics and astronautics, they've introduced that course for students choosing to emphasize propulsion as their area of study and concentration. Haifeng is also a member of the Combustion Institute, the American Physical Society, and he's a member of AIAA, the American Institute of Aeronautics and Astronautics. So with that, I'm pleased to present to you my colleague, Haifeng Wang.
All right, thank you, Bill. Can you hear me?
I can hear you.
Okay, all right, thank you, Bill, for your kind introduction. All right, so today I will talk about my research in turbulent combustion modeling. I will do a little bit reflection and then think about how to move forward. All right, so turbulent combustion, it's a problem, it's a phenomenon that is widely observed in a lot of applications, like in internal combustion engines, aircraft engines, heavy-duty constructive vehicles, industrial furnaces, power plants, rocket engine, and even in natural disaster like the California fire. So this is a problem that is widely seen, widely observed, and being able to predict this phenomenon is going to be a very, very important task. So my research focus is really to develop models for turbulent combustion and how to use modern high-performance computers to predict this behavior. So when we do simulations, typically this is how we do. We choose a mesh and then we discretize the equations, governing equations for this problem, and then we get like a set of algebraic equations, and then we put that on a computer cluster, and then we conduct the simulations. So this is the typical way how we do this. And for turbulent combustion, unfortunately, we found that in order to resolve all the details in a turbulence and combustion problem, in order to resolve all the details, we need to have a very, very small grid, and the grid resolution is denoted here as eta. That is sort of the smallest time scale and smallest length scale involved in this problem. And we know that this length scale is extremely small. So even conceptually we can do this, but practically it turned out to be infeasible. It's not, it's a computational cost is just too expensive. And instead, a more practical picture or feasible picture is something like this. We have to use a relatively large grid to solve this problem. We can do that for practical devices, but in this case, the grid size that we have to use is actually much larger than this length scale that we need to use to resolve all the scales. And then the question is, how do we construct the subgrid scale information? So this information at the subgrid level is simply lost because we don't have the representation of that length scale by using the grid that we're using. So this is just like you have a low resolution photo, and then you want to reconstruct a high resolution photo, and that sounds like an impossible task, or at least a very, very difficult task. So unfortunately, a lot of the important physical processes like subgrid scale turbulence, molecular diffusion, chemical reaction, all of these physical processes, they occur at the subgrid level. So, to construct the information at the subgrid level for all these different physical processes, it is important, it is needed to provide a closure to the simulation that we need to conduct. And my area is mainly focusing on small turbulence molecular diffusion, chemical kinetics, and how to reconstruct this information and the coupling between these different physics. All right, so next I'm just going to use like a few examples to quickly illustrate the kind of work that we have been doing. The first example is to think about differential diffusion in this so-called Fleming model. So differential diffusion is a phenomenon that is widely observed simply because different scalars in combustion they have different diffusivities. So this causes this so-called differential diffusion. In traditional models, in traditional combustion models, for a good reason, we have to introduce equal diffusion assumption. And that is needed to construct some of the models. And one example is this so-called Fleming model. To construct that model, we have to introduce equal diffusion assumption. And we have been using that for like 30, 40 years. And nowadays, when we think about combustion, obviously molecular diffusion is a very, very important process. So the question, how do we incorporate differential diffusion in our modeling? So recently we invented this series of new models. We call them LDD, NDD, or NDDV models. And the idea is to try to incorporate differential diffusion in Fleming model. So here, just a quick example to illustrate, how these models work. So this is a very simple mixing layer test case in a box turbulence. And here, Z is like a parameter we use to quantify the differential diffusion effect. These circles, you can think these are like an exact solution for this highly simplified problem. So the new models, they work pretty well. We are very close to the exact solution. And this is just for comparison. This is a traditional model. And you will see that this model over-predicts the differential diffusion by at least 1 order of magnitude. So you can see that this is a very important progress we made in terms of how to incorporate differential diffusion. So this is another example. So in this approach called transport PDF particle method, so this is a very sophisticated modeling approach for turbulent combustion. So basically we're using a lot of particles to mimic the combustion process. And all these particles, they evolve stochastically in the physical space, scalar space, so that we can mimic the evolution of PDF in this problem. For treating the molecular diffusion, we actually have a similar story. So traditionally, we have to assume equal diffusion. So this random walk model, it is basically an equal molecular diffusion model. And then in 2008, 2007, there's a new model that was invented to try to incorporate differential diffusion. But unfortunately, all these models, they turn out to be not convergent in the sense that when the number of particles goes to infinity, the error does not go to 0. So it's inconsistent and non-convergent. You can see that this is a random walk model, a traditional model, and this blue color is another model called mean shift model. So the y-axis is the error, prediction error, and x-axis is the number of particles. So theoretically, when the number of particles goes to infinity, the error should go to zero. But in this case, neither the red color model and this blue color model, neither of them is convergent. And then we invented this so-called VCMS model. Basically, we achieved this nice convergent behavior. And this is another example to deal with a slightly different approach called Aurelian multicolor fields method. And it has a similar story, and some of the models are not consistent, and then we try to achieve that consistency. And I will just skip this and go to the next example. In this example, we are dealing with the modeling of mixing in turbine premix combustion. So mixing is extremely important in turbine combustion. It determines how fast different species they mix, and mixing will a combustion can only occur when all the species or scalars they mix together. So mixing is a very, very important process. And in order to model mixing, we did some very detailed analysis, lengthy analysis. We found that somehow, if we can validate a hypothesis like this, we will be able to develop a very good mixing model. So the hypothesis is like this. So a factor called F, that is called a scaling factor F, if it is a power law like this, in which delta is like the grid size and delta TH is the flame thickness. If this F factor is a power law, then we know that we can develop a very good mixing model. So it is very important to test this hypothesis. So then we try to test this hypothesis by using a DNS flame that we obtained from Sandia National Lab. So we formulate the different quantities, and then we try to test the hypothesis. And indeed, it turned out that this hypothesis is indeed true, as indicated here. So the F factor against this delta divided by delta TH, and we found that if this number is not very small, we indeed observe a very remarkable sort of power law scaling in this log scale, log scale. It shows as a straight line. So that strongly supports the hypothesis that we formed. And based on that hypothesis, basically we can build a model that has very, very strong theoretical basis. So the model we built is something like this. It looks very simple, in which A and B, these are the model parameters. We calibrated these model parameters based on the DNS data. All right, and then we published this work recently. And then after we published this work, we looked at this model. We found that this model actually didn't work very well. And one important reason is because we found that these calibrated model parameters A and B, they're not good enough. And then the question is, how do we further enhance this model? So the idea we had is to use machine learning to construct better models for A and B, these model parameters. And indeed, that was a very, very good choice. And just to illustrate the performance, so look at this subplot. You'll see that these circles are essentially the DNS data. You can think these are like a true solution. So the green line is actually the model we developed early with this calibrated A and B. The model actually didn't work very well. And later we used the machine learning model, which is this blue line, the red line. You will see that this red line agrees with the DNS data very, very well. So that shows that this machine learning model can enhance this physical model very, very well. So machine learning actually is a new direction that we have identified to help enhancing the model development. And currently, we have quite a few efforts in different aspects to utilize machine learning for the model development. So this is just a quick examples for developing the wall models for hypersonic boundary layer, to develop a convective heat transfer model for a wall fire. And this is a collaboration with the insurance company. And this is to develop a reduced order model for emission predictions. And this work collaboration with Honeywell. And this is a DOE project in which we will use machine learning to enhance the model for the prediction of this so-called turbulent jet ignition. So this is just an example, and a lot of this work, all this work involves machine learning. I think I'm running out of time, so I need to go a little bit quickly. So moving forward, we will still focus on turbine combustion and further enhance the models that we're developing will strongly rely on physics-based approaches, but at the same time, we're going to follow ideas from data-driven machine learning for the further enhancement of the models. And in terms of teaching and service, I'm teaching two courses currently. One is the undergrad level course, thermal sciences, as Bill mentioned, and the other is my grad level course, it's turbine combustion modeling. Next semester, I'm going to teach a new course called computational combustion. It is sort of a modified 1690 to make it a little bit easier so that it is more accessible to many students. This is a course that I'm planning to teach, and the idea is that I hope that we can use this course to help building computational capabilities or skills for our undergrad students before they go to their job market, job position. And internal surveys, I'm very grateful to my department head and a lot of senior faculty in the department to give me feedback and suggestions in terms of how to enhance the service level, which is important as a tenured faculty. So with that, I will stop here and thank you very much for your attention.
Great. Thanks, Haifeng.
Sorry,
I
I'm
think
running a little bit longer than.
there's a little bit less time for questions and answers, I guess, then. So I'm supposed to help moderate Q&A. So the way we'd prefer to do this is if you have a question for Haifeng, you can raise your hand and I can call on you. And I think I'm a co-host that I can help unmute you if you're stuck. Or if you must, you can use the chat window. But I think we'd prefer if you had a question for Haifeng, you raise your hand and you ask directly that way. So I need to change my view so I can see everybody.
Yep, absolutely. And actually for the Q&A, if folks want to turn on your videos to, replicate a nice room over in Fu where we would normally have these and have a sense of community, please feel free.
So I should have a sandwich in my mouth too while we're doing this, then that would be the truth.
That's right.
So Haifeng, one of the things I know you're doing is getting involved with the machine learning. So which kind of algorithms are you finding to be most productive for enhancing your models?
That's an interesting question. The models that we're using right now, it's very basic. We use something called random walk. It's a basic machine learning model. The focus is really just the application of machine learning. So we did try, other models like a neural network, those deep learning, those kind of models. For the problem that we're dealing with, we didn't find a significant difference among all these different models. But still, that is an active research area. I think that getting deeply into machine learning model and seek models that are suitable for the physical problems that we're dealing with. It is a direction or research area that needs to be taken care of.
Yeah, one of the interesting things is sometimes you can have a simple model that doesn't do a very good job, but it's very explainable. Mm-hmm. And as you go to deeper levels of learning, then the model doesn't give you very much explanation. It's just curious about where that balance might fit for you.
Yeah, it's a very challenging thing to do because when we deal with the models, we always emphasize physics. But now when we use machine learning, we sort of lost our insight about the physics. So that's a very challenging thing to do. I think at least currently our thinking is this. We will still try to retain the physics that we know, the physical insights that we have about the combustion problems. We will not lose that, but we will use machine learning as a tool to assist the model enhancement. So that is sort of the position that we put right now. We will probably not jump into like a purely sort of a machine learning data-driven model for combustion. We're not ready to do that yet.
Good, thanks. Other questions for Haifeng? Yeah, Arvin's got his hand up. I can see you visibly. I don't know if there's a. Go ahead, Arvin.
I didn't get my. I couldn't find where the Zoom hand is, so I'm just going to raise my hands. Really nice presentation, Haifeng. I wonder if in getting to where you are, you've had many successes, right, Haifeng, on the route to getting here. What stands out to you today as one success where you felt really good when you went back home and it was good? And if you could maybe say something about what were the keys to, what is key to achieving that particular success? If you could just reflect on that a little bit. Over.
Okay. All right. So that's a very nice question. So first of all, what I view that is sort of most success, I feel that I really achieved something. I think that is something that I feel very, very different when I was like a graduate student. When I was a graduate student, I feel that I achieved a lot. When I published a paper or 2 papers, I feel that it was a great success. But in my position, when I look back, I continue to publish. But more importantly, I think the success that I can strongly feel is the students I have. Their growth, their publication, and they, after they receive their degree and get a job position. I think that is the most success that I can feel. And then in terms of how to achieve that, it's obviously very challenging, and I think everybody has their story, and I have my story, and particularly in my case, I don't think it's a smooth journey. It's a very challenging thing, and starting from the beginning, taking a student and work with a student, a lot of challenges out there. But I think that's one thing that worked for me. That it worked for me. One particular thing that worked for me well is this, never give up. I had a lot of difficult moments. I almost thought of like giving up, but I never give up. Persistency is probably the only thing I want to say. That is the strongest thing that is driving me moving forward.
So is that your hand up or is that applause, Arvin? I'm just trying to make sure I can interpret that too.
Oh, that's an applause. Sorry.
It's the applause. That's okay.
Thank you.
We're probably short on time, so maybe I should turn it back to you, Arvin, or do you want to try? If there's another question, I guess we could squeeze one more in, or just turn it back.
Yeah, another question you can squeeze in.
I don't see anything in the chat window, so. All right, well, let me go ahead and turn it back to you, Arvin, so we don't take too much time from the rest of our speakers today. But thanks, Haifeng. Congratulations, as that's the part of the celebration here. So thanks for letting me be part of this with you.
Thank you.